Alright, so in this video we are going to look at matrices as functions. We have seen them in many different facets. We've done Gaussian elimination with them. We have solved matrix equations. We've done a lot of things with matrices so far. And the final thing that we're going to do is look at them as functions. So what we're going to talk about ultimately is how a matrix can transform vectors. So our new input, and rather than a constant or some value, some numerical value, we're going to be plugging in vectors into matrices, and that's going to do something. Specifically, it's going to transform that vector in some way. And so we're going to look at all the different ways you can transform a vector using a matrix. So with that said, let's go ahead and get started. All right, so I want to start by looking at the vector 5, 2. All right, we can describe this vector rather in vector notation. We can describe it in column matrix notation. So column vector 5, 2, and I want to see what the matrix 1, 0, 0, -1 does to this vector using multiplication. So we're going to operate on this vector using this matrix. Let's look at what. Let's go ahead and call this thing x. Let's go ahead and look at what a times x is. Okay, so we got 1, 0, 0, -1. We got 5, 2. And what does this do? So 1 times 5 plus 0 times 2, that's 5. And then 0 times 5, 0, minus 2. So what this matrix does is it takes in a 2 by 1 matrix or a vector and spits out a different 2 by 1 vector. So this matrix A has a functional property that it takes in 2 by 1 matrices and spits out 2 by 1 matrices. And that second matrix, that second vector, is different now. How is it different? Let's look at it graphically. So we have the vector 5, 2. So 5, 2 is going to look kind of like this. And then we have the new vector 5, -2. So you can kind of intuitively realize what this matrix has, what this matrix property is. What functional property does it have? It looks like it's reflecting over the x-axis. Let's just double check that with another example. So here's another vector, -3, -6. All right, that can be rewritten as the column vector. All right, let's find out what a times, let's call this thing y. Let's find out what a times y does. So 1, 0, 0, -1 times -3, -6. Just do it out. 0 right there. -3 and then +6. So once again, this matrix took in a vector, spat out another vector, and I believe that vector is in fact a reflection over the x-axis still. So we have -3, -6. That's going to be this vector down here. And we have -3, 6. That's going to be this vector up here. And we are once again reflecting in the opposite direction over the x-axis. So it turns out that the matrix A that I had on the previous page, this thing right here, has the property of a reflection over the x-axis. It takes vectors and reflects them over the x-axis. I'm going to quickly do this just in general. So let's take the general vector, xy, and then let's just find out what a times this vector is. Let's call this vector like vector u. So a is 1, 0, 0, -1. U is xy. And then just doing this out, I'm going to get x comma -y, which, if you remember from geometry, is a reflection over the x-axis. So this, in fact, does have that property. A has the property that it takes in a 2 by 1 matrix and spits out the 2 by 1 matrix that is a reflection over the x-axis. Cool. So we are looking at matrices as functions, specifically transformational functions. All right, what I want you to do is, here's another matrix. It's another 2 by 2 matrix. I want you to tell yourself, so pause the video if you need to, tell yourself or figure out through just doing it what this matrix function is. How does this operate on a 2 by 1 matrix or a vector? All right, so I'm going to use the same old vector I used last time, 5, -2. I'm going to go ahead and do this out. I'm going to get -5. I'm going to get 2. Oh, sorry, not 2, -2. And graphically, what I'm seeing here is I have the vector 5, -2 over here. And then it becomes -5, -2. So now it looks as though the matrix -1, 0, 0, -1 has the property of a reflection over the y-axis. All right, so these are pretty straightforward, pretty simple. We can get much more complicated. But there you go. And we could show this in general using a xy vector. If I had done this with xy, I would have gotten, what have I gotten? Let me just do it real quick. I would have gotten -xy, which is a reflection over the y-axis. All right, I got a few more for you. Actually, before I move on, I do want to say this. If I'm going to start calling these functions, I mean, we can have some function notation. So what's the function notation here? So we are inputting vectors. So we have a function. We're inputting a vector. And what does this look like? The function is something along the lines of this, and then you have the vector there. So you plug in a function, you get out a vector. You plug in a vector, you get out a new vector. All right, and we don't know what that is. It depends on what you plug in, and you can plug in an infinite amount of these, and we can create pictures, which is kind of what we're getting towards. This is kind of similar to if I said, hey, the function of the real numbers is like, I don't know, 2x, right? So you plug in something, and then this ends up being a line with slope 2. But the question is, what are these things going to be? Let's keep going. So what if I wanted to do multiple points at once? So let's say I have the matrix -1, 0, 0, -1. All right. Let's real quick figure out what this does. So let's take any old vector xy and then do it out. So we get -x, -y. All right, think back to geometry. What is this transformation? It is a 180-degree rotation. All right, a rotation needs a axis, so 180-degree rotation about the origin. All right, that's some old news. But what if I want to transform not one, but a multiple set of vectors? Can I just do this all at once? Let's say I want to transform the vector 5, 2. Let's say I want to transform the vector 4, 3. And let's say I want to transform the vector 1, 2. Is this going to work? Is this going to rotate all three of these vectors all at once? And before we do it, let's just double check that our dimensions check out. This is 2 by 2. And this is 2 by 3. This could be 2 by n. It doesn't really matter. We can do this. Let's see what happens. We have -5, -2. We have, which is a rotation. The point 5, 2 is now gone to -5, -2. All right, the next one we're going to have -4, -3. And then we're going to have -1 times 1 is -1, and 0, -1, that's going to be 0 minus 2, that's -2. All right? So we can take in multiple vectors at once and output a set of multiple vectors. That's really cool, because what if I want to do this with 1,000 vectors, which is often the case? I can use this to rotate a collection of vectors all at once. So that's cool. And this, once again, this is a rotation, as we said, but if I want to reflect a bunch of vectors over the, I don't know, x-axis, I gotta go, where is it? Back to this one. So it just depends on the vector you want. Sorry, the matrix that you want. What operation do you want to happen to the vectors? All right, we can do this with multiple vectors at one time. I want to real quick get a quick picture of what's going on here. So let me go ahead and draw a little grid. All right, so what did we have previously? We had the points. We had 5, 2. So 1, 2, 3, 4, 5, 2. I'm going to be a little bit relaxed about this. 5, 2. We had 4, 3. So 4, 3. We'll call this point A. I'm going to call this point B. And we had 1, 2. So that's going to be about right there. And I'm going to call that point C. And what happened to these? So A became -5, -2. B became -4, -3. And C became -1, -2. All right, I'm going to call this A prime, B prime, C prime. All right, so what does this matrix do? It rotates around the axis 180 degrees, and it's doing that to an object. All right, imagine that I was describing every single point on this vector, and I've rotated this triangle 180 degrees. So this matrix not only has the ability to rotate vectors, but it also, if you start thinking about vectors composing up other objects, it can rotate objects. So the matrix -1, 0, 0, -1 had the property that it rotated this triangle 180 degrees, which is cool, because imagine these things expanding more and more and getting more complex. Imagine like a really old, like early 1990s video game, like, I don't know, Pokemon Red or something like that. Like the image wasn't super complex on the screen. So like what's happening is, if like you have a character looking this way and you want them to look the opposite way, like we're not going to change anything else about this character's image besides like where the eyeball is, so that the person playing the video game sees a character looking in the opposite direction. Of course, this is much more complicated now, but you know, processors are much more powerful now. But let's say this is the image that you wanted to create. You had an image right here, and you wanted to make it this. You had this pre-image, and you want to create this image. What do? Well, you take every single pixel on this character and you reflect it over some axis. So we want to reflect this over the y-axis. If I remember correctly, I believe we just showed that this is a reflection over the y-axis. All right, so this is a really simple case, but it's going to expand, and we are going to be able to make much more complicated pictures. What, this is probably like, I don't know, 16 pixels. Imagine having, I don't know, like the matrix 1, 0, 0, -1, the reflection, and then multiplying that by 1,000 columns. How many pixels are on a modern television? I don't know. 1080p. I don't know. The concept of the matrix as a function is used extensively in graphics, if that's something that you're interested in. All right, so moving along, here are 4 matrices that I want you to inspect and tell yourself what they do. So here's one, switching it up a little bit. Ooh, oops. What does 0, 1, 1, 0 do? What does 0, 1, negative 1, 0 do? What does 0, negative 1, 1, 0 do? And then what does 0, negative 1, negative 1, 0 do? So take a second to figure out what each of these matrices as functions do to a 2 by 1 vector. I'm going to go ahead and proceed. So I'm just going to do it with an arbitrary vector xy. So if I have the vector xy, what does 0, 1, 1, 0 do to it? So 0 times x is 0 plus y, and then x plus 0. Oh, this switched x and y. All right, what does that do? You can either think back to geometry because you've learned this before, or you can just like draw a picture, which is 99% of the time what you should do. So let's say we have, I'm going to use the first quadrant for my xy. So let's say I have x comma y. All right, what does y comma x look like? That's going to be, ooh, this isn't the best picture. Let me rewind. Haha, because now you might know exactly what it does if you didn't already. All right, yx is up here, and this is a reflection over the line y equals x. So 1 is a reflection over the line y equals x. A reflection over y equals x. All right, let's see what this thing does. Okay, xy. All right, it's going to become, let's see, y and negative x. All right, so several things are happening. The coordinates are switching places, and the second one is becoming negative. This may ring a bell from geometry as well. Let's just like do it out and figure out what's happening though. All right, so I'm going to change the color up so it doesn't get confusing with this top picture. So I have the coordinate xy. I'm going to use the same one. All right, and here now I have y. So y is small, and x is now negative. So I'm going to be down here far, and it looks as though this is a 90-degree rotation. So I'm going to go ahead and write that over here. Right, that was 0, 1, negative 1, 0 seems to be a 90-degree rotation. What is that? Clockwise. About the origin. All right. All right, I'm going to keep going. All right. Hopefully you already did this, and you can just say fast forward through the video if you already know what these two do. Let's go ahead and look at, change up the color again. This one. Progressively getting better in terms of differentiating the problems. All right, so we're going to have negative y, and we're going to have x. So similar to 2, what's happening here? Let's draw a little picture. And we have this vector, x comma y. And then we have now, we're going to have a small y and then a large x. That's going to be up here. And as anticipated from my point of view, this is in fact a 90-degree rotation. Now, this is to be expected. It's very similar to number 2. Counter. Clockwise. about the origin. Cool. And then what's this last one do? Go ahead and guess if you haven't already. I'm going to go ahead and do it. Let's do this in light blue. I find dark blue is kind of hard to see. I've learned that the hard way. All right, so we have x, y. And we have, that's going to be negative y, negative x. This rings a bell from geometry, but that's unfair because I taught geometry for several years, so it's drilled into my brain. You only learned it once. All right, so we have x comma y. That's going to be over here. And then now we're going to have a negative y, negative x. So that's going to be down here. I'm kind of going off the page. All right, my picture actually doesn't do this one justice. This is a reflection. Over y equals negative x. I wish my picture did a better job, but I ran out of room here at the bottom. I could be a little sneaky though. I'll do this. Cool. All right, so these just 4 more matrices that perform different operations on vectors. All right, we have a reflection over the y, y equals x. We have clockwise rotation, counterclockwise rotation, and a reflection over y equals negative x. All right, let's look at, here's another one, a little bit different than the previous ones. Let's look at 3003. All right, so let's do this once again on that convenient vector 5, 2. What happens? All right, so we're going to get 15 plus 0, 15. And we're going to get 0 plus 6, all right, which is 3 times 5, 2. So what is this function doing? What is it doing to a vector, and how is it changing the output? All right, this is the first matrix that we've looked at that is changing the length of the vector. All of the other transformations that we've done have been rigid transformations. This is the first one that is actually dilating the figure. So we have this. This vector 5, 2. And this thing is turning it into 6, 15. So as you might be able to anticipate, these matrices can become much more complicated. We've only dealt with 1s and 0s, and now with a 3 and a 3, but I could put like a 6 and a 7, a 3 and a 47 here, and we need to know what that does. And the way we do that is we look at what this matrix does, not to 5, 2, but to our I and j vectors. So what does the matrix 3003 do to 1, 0, and what does it do to 0, 1? And we are going to see that that is enough to understand a 2x2 matrix and its function. So what does 3003 do to 1, 0? It dilates by 3. What does 3003 do to 0, 1? It dilates by 3. All right, we could have instead looked at this just holistically. 3003, what does it do to 1001? And that's going to give you 3003. All right, we're getting towards a big idea here. This seems kind of silly right now, but bear with me. All right, let's look at this graphically. All right, so let's say I have like those I and j vectors. So we have I and we have j. All right, what happened here? So I and j, what this is describing pictorially is a square, right? And then if I look at how these were transformed, now I have a 3 j's and 3 i's, and I have a square that has been dilated by 3 as well. And this is kind of the way we're going to start looking at how a 2x2 matrix affects a set of vectors, right? What does it do to I and j? So to close up this page right here, what does the 3, 0, 0, 3 matrix actually do? It dilates a unit square by 3, all right? It takes area 1, makes it area, what is that going to be? 3 by 3, 9. So it's dilating. The area is changing by the square of the dilation. But we're going to look at how the unit square is being changed. All right, we could have done that on the previous pages. How do each of these things, how did 1, 0, 0, 1 affect ij? How does 1, 0, 0, negative 1 affect ij? We could have talked about it in terms of the unit square, but I wanted to build up to this. Right, this is kind of how we describe what each matrix does. How does it affect the unit square? All right, new 2x2 matrix. Let's see how the matrix 1, 2, 0, 1, so progressively more complicated. Started out easy. And not to say this isn't necessarily easy, but it is, I think, arguably more complicated. How does this affect the unit square? And once we know how it affects the unit square, that's how we're going to describe this matrix function. All right, so let's see. We have, well, let me go ahead and draw this picture first. All right, so we have one. Let me go ahead and get purple. We have this square, this unit square. All right, and we want to see how the output looks like. So I'll do that in green. So 1 times 1 is 1, plus 0, that is 1. 1 times 0 is 0, that's going to be a 2. All right, 0 times, that's going to be a 0. And 0, that's going to be a 1. All right, so these are our new vectors, 1, 0, and 2, 1. So 2, 1. That could have been better. And let's go ahead and fill out this quadrilateral. What is this as a parallelogram? That is going to be that. And there you go. So what does the matrix 1, 2, 0, 1 do? It is what we call a shear. Notice that this square has been stretched its x values have been stretched, but its y values have not been stretched at all. So it's kind of like a dilation, but only in one direction. All right, this figure has been changed. Notice that its base is still 1 and its height is still 1, so its area is still 1. Shears are area preserving, but they're not non-rigid though. All right, so 1, 2, 0, 1, that is a non-rigid area preserving transformation function. Let's look exactly what this thing did, though, in general. So let me go ahead and set myself up. So we have a matrix 1, 2, 0, 1, and we're looking at what it's doing to an arbitrary vector, x, y. And let's see, we're going to have x plus 2y here, and we're going to have y here. So y is unchanged as I previously said, but the x-coordinate is now you're maintaining the same x-coordinate, but then you're adding to that x-coordinate 2 of the y-coordinate at that spot. So this is what a shear is doing algebraically. If I have a little like picture, if I have the vector like, I don't know, 2, 3. Right, its y is not going to change, but its x is going to become, its x is currently 2, and we're going to add 3 times its y. So we have 2, and we're going to add 6. So 2, 3, 4, 5, 6, 7, 8. That is what a shear is doing to a single vector. But when we look at the matrix 1, 2, 0, 1, we say it's a shear, and it's changing the unit square to become this parallelogram with equal area. But yeah. All right, so this whole time we've been looking at given a matrix, what does it do to an arbitrary vector? Let's look at an arbitrary matrix. What does an arbitrary matrix do? All right, so I have a matrix A, B, C, D with whatever numbers you want in there. And how do we know what this thing does? If I go back to this concept over here, we are looking at what it does. Here we go. What it does to the unit square. So let's go ahead and do that. Let's find out what this does to the unit square, and then we will know the function of this matrix. All right, so what's this going to be? It's going to be a times 1 plus 0, a times 0 plus b, c. All right, this is not very challenging to compute. What happened? All right, the vector 1, 0 went to AC, and the vector 0, 1 went to BD. So what is this saying? If you give me a matrix and you want to know what it does what the matrix that you gave me says. If you gave me a matrix 47, 3, 6, 21, what does this matrix, what is its function? What does it do to a arbitrarily given vector? It takes the vector 1, 0 and takes it to 47, 6, and it takes the vector 0, 1 to 321. So whatever that is what the operation is. The first column of your given matrix is what it does to 1, 0, and the second column is what it does to 0, 1. We call this the matrix basis theorem. All right, kind of in reverse, if what this does for us is if you want a matrix that does a specific often complicated transformation, all you have to do is figure out where 1, 0 and 0, 1 map to. That's all you need to figure out. That's what the matrix basis theorem is saying. All right, let's use this in practice to kind of justify why it's actually pretty awesome. All right, so let's say you want a matrix. You want a matrix that rotates all vectors 90 degrees. Let's go with clockwise. Less letters for me to write. All right. Yes, I know you already know this, but let's pretend like we didn't. You want a matrix that rotates all vectors 90-degree clockwise. What your goal is you need to figure out the image of the 1, 0 vector and the 0, 1 vector. And then that is your matrix that does the rotation. So let's say I have the vector 1, 0. All right, a 90 degrees clockwise rotation goes here. So I want a matrix that rotates 90 degrees clockwise. So that matrix is going to be, I'm going to call it M. All right, what's the image of 1, 0? 0, negative 1. Right? What is the image of 0, 1? 1, 0. Right? There is your matrix that rotates 90 degrees clockwise. Right? We didn't have to figure it out just by doing. We just took 1, 0 and 0, 1, and we looked at the images, and this is the matrix that rotates 90 degrees clockwise. All right, something a little bit more complicated. What if you want a matrix that rotates, you want a matrix that rotates an arbitrary amount of degrees. So theta degrees. Let's go counterclockwise. All right, we're going to use the matrix basis theorem to figure out what the matrix is that rotates theta degrees. I have a vector. 0, 1. Sorry, 1, 0. All right, it's being rotated theta degrees. Right? This is currently the vector 1, 0. What is this vector? All right, once we figure out where 1, 0 is going, that is going to be the first column of our matrix M that does the transformation that we're looking for. So we're going to use right triangle trigonometry to figure this thing out. All right, this is a right triangle. All right, its x coordinate is cosine theta, and its y coordinate is sine theta. So I'm going to put a cosine theta here and a sine theta here. All right, now we need to figure out where the vector 1, 0 is going. So now it's going over here. All right, what we know is that this is theta. We need to figure out where 0, 1 is going. Some more right triangle trigonometry. So if this is theta, this thing right here is going to be sine theta, and this thing is going to be cosine theta, right? Oh, no, but this is going to be negative sine theta. Almost had that wrong. So what is this coordinate right here? It is going to be negative sine theta, cosine theta. So I'm going to go ahead and put that over here. Negative sine theta, cosine theta, right? This is the matrix that rotates an arbitrary vector, an arbitrary degrees counterclockwise. Right? You give me the amount you want rotated, put it in here. That matrix is going to rotate that far in the clockwise direction. All right, this is actually potentially worth memorizing. This matrix right here. This has the power to rotate vectors theta clockwise. All right, the last thing I want to do in this video, I want to talk about, hey, what if you want a matrix that takes the 0.45 to 14, 17 and takes the 0.21 to 4, 7. All right, how can you figure out what this is? All right, we're going to kind of use a corollary of the matrix basis theorem, but what we need is we need a matrix A, B, C, D. Take a second to try to figure this out, by the way. All right, we need a matrix A, B, C, D that takes, 4, 5, 2, 1. Messing up all over the place here. We need to take that to 14, 17, 4, 7. All right, how are we going to solve this thing? We are going to use matrix multiplication. All right, so we got X here. Let's go ahead and call this thing capital A. We'll call this thing capital B. How can I solve for X? We're going to right apply by the inverse of A, and that'll leave us with X. And the next thing you know, we have a matrix that does what we want it to do. Takes the points 4, 5, and 2, 1 to their respective coordinates, and all other points to their respective coordinates using the same transformation. All right, so let's just do it. What is a inverse? All right, I'm going to do that on the side here. A inverse is going to be 1 over the determinant, so 4 minus 10, that's negative 6, times switch, so that's going to be a 1 and a 4, and a negative 2 and a 5. And then I'm going to jump to the next page now. I am doing negative 6, 1, 4, negative 2, negative 5, times. Oh, I'm messing up. Think about what I did wrong. All right, if you're following along, hopefully you did it right before I even attempted it. I need to right apply, or I'll get the wrong answer. So I'm doing 14, 17, 4, 7. And 1, negative 2, negative 5, 4. And that 1 over negative 6 can go out in the front since it's just a constant. All right, so let's do this thing out. We got 14 minus 20, that's negative 6. This is all going to be divided by negative 6 out here. We got 28 plus 16, which is 3242. Oh, sorry. That is not 42. That's going to be negative 28 plus 16, which is a negative 12. And then we're going to have 17 minus 35, which is negative 18. And negative 28 plus 28, which is, negative 34 plus 28, which is negative 6. I'm going to hit all of these with a negative 1/6, and we're going to have a 1, positive 1, positive 2, positive 3, positive 1. All right, and this matrix takes the coordinates 4, 5 to 14, 17, and 2, 1 to 4, 7. I'm just going to double check that that actually happens. So 1, 2, 3, 1 times 4, 5, 2, 1. All right. 4 plus 10 is 14. 12 plus 5 is 17. All right, looking good. 2 plus 2 is 4. And 6 plus 1 is 7. So there it is. All right. Matrices as functions. We talked about all these matrices that have ones in them and how they have these basic rigid operations. We talked about the shear. If you start throwing other numbers into a transformational matrix, it's going to start changing the rigidity of the square matrix, but it won't be changing the area. It's area preserving. And then we talked about the matrix basis theorem and how if you want a matrix that does something specific, all you need to do is look at the unit vectors I and j and how they are transformed. And then we did this last problem here at the end that if you want to know where specific coordinates are going, you can find the matrix that does that as well. So there you go, transformational matrices.